To quantify the differences between I/O access versus memory read access, we collected some data in a little experiment here. So here we have two different PC systems. You can see the results are similar. These are different architecture, different chipsets. And here, as you would expect, cache read access is very, very fast. So this is done by polling repeatedly as aggressively as possible, and then looking at how long it takes to do a number of transfers and dividing it by the number of transfers. And so this gives you average read latency. And then you do the same thing, only locating the data out in DDR memory space. And you can see that there is more than an order of magnitude difference. If you compare that again to the PCI Express endpoint read, so this is an I/O read that's going outside of the chipset and to the I/O device, it's another order of magnitude yet again. Now if you look at interrupt latency, the factors that affect interrupt latency, one of the tendencies in processors is deeper caches, larger caches, more cache layers. Now this helps to increase throughput, but it actually doesn't do much for you in terms of interrupt latency, especially considering that that the penalty for a cache miss, when you have a more complex cache hierarchy, the penalty can be quite large. So what this does is it makes your interrupt latency much less deterministic and much less predictable. So that is, the difference between the minimum latency and the maximum latency gets worse. And this is something that I believe will continue to get worse in the future. Also, deeper processor pipelines means that there is more context to be stored. So when a context switch needs to happen, that pipeline needs to be flushed, and that leads to longer latencies. Now we did a little experiment to illustrate how latency is distributed. So this is where we used a test endpoint card to generate an interrupt, and then repeatedly measure the time interval between the assertion of the interrupt and the deassertion from the interrupt handler. So this time difference here. And then the other thing we did is to vary the amount of system loading and observe how that affects the interrupt latency. So there are three sets of results here. One is with system idle, so that is where we're running this test without any CPU loading except for the just some background tasks and the application to do this measurement. And then we loaded up the system with high CPU load, that's the red bars. And then we did another experiment where there's less CPU load but a lot of I/O loading. So you can see from the blue bars, the system idle, that the blue bars are distributed very much on the left-hand side as you would expect. And here the maximum latency that we observed was 33 microseconds. So this is pretty fast. This is pretty good interrupt latency. Now when we perturb that by running a CPU intensive application, you can see that the maximum has increased very, very significantly. Here you can see that there's some distribution peaks in the way that interrupt latency occurs. You can see some of them occur very quickly, some distribution here, and then some outliers that are even beyond this chart. So that's 18.2 milliseconds versus 33 microseconds. Now what's even more interesting is the fact that here we did another experiment with lower CPU load, and yet the maximum is even greater. That's because this was done with a very disk intensive, this was a virus scan, and disk activity seems to perturb it even more. Not really that surprising. So with that in mind, if we look at a simple DMA servicing scenario, this is where the host is going to set up a transfer. It's going to kick off the peripheral, which is going to act fairly autonomously while it's doing its DMA or sequence of DMA transfers. And then at some point, the system is going to get interrupted to go and set up additional DMA transfer. Now, if this latency here is too long, then buffers, FIFOs are going to run dry or overflow, and that means dropped frames, it means skipped audio, and so on. So if we're going to solve the latency problem by ensuring that we have enough buffer size, then you can look at this, you can model this in a very simplistic way. Here we have a series of lines for various latencies and throughput in megabytes per second and the required buffer size. So if we take the example of a single stream of 1080p 60 digital video uncompressed, here that's about 250 megabytes per second. Now if we had a millisecond of latency that we needed to build into our buffer, then you can see that would require a buffer of around 250 kilobytes. So that's not a lot if you're considering DDR memory, but for on-chip buffering, that's a pretty significant amount of memory. And if you remember, we're talking about interrupt latencies that we saw previously in the tens of milliseconds. So if we consider the DMA engine architecture for PCI Express, there are a couple things we want to consider. PCI Express is a full duplex link. It's got an upstream and downstream that can operate simultaneously, and that's something we want to take advantage of. Also, we will typically want to be able to handle multiple upstream and downstream DMA threads or channels. However, only one of those is going to be able to be live on the link at any one time, so those need to be multiplexed.